Welcome. I'm Dr. Ferdinand. Physics has to be one of the most fascinating sciences, and the reason is because it explains so much about our universe. The physics for the MCAT exam is at the introductory college or university level, and so the equations and the concepts are quite basic, but it is very important to understand the information. It will allow you to ace this part of the exam, because it is a part of the exam that many students do not prepare adequately for. All the equations that we discuss will need to be memorized. That is very important, and that is a basic part of your learning. Now, the plan is that we're going to start by talking about the atom, because it is the most basic structure of our universe. And then we're going to talk about aspects of the atom, which are electrons, and their motion, which is electricity. Then we'll go on to talk about waves and light, problem solving. First, the atom. Now, it's important to say that we're going to discuss more details about the atom in general chemistry when it comes to electronic structure and the shape of atoms and molecules. But for the moment, it would suffice to say that the basic atom is a structure containing a nucleus, and the nucleus has neutrons and protons. Neutrons being, of course, neutral particles, and protons being positive particles. Around the atom is a cloud of electrons. Electrons having a much smaller mass than either neutrons or protons, and having the opposite charge of a proton, an electron being negatively charged. Now, you would have to imagine that if you have an atom with its positively charged nucleus, negatively charged electron cloud, and opposites attract, and therefore there is a lot of energy, a lot of force involved with this atom. We call that an electronic force. Within the atom, there are a number of protons, and these protons are being held together. And imagine, if opposites attract and like charges repel, then these protons, which are within the nucleus, repelling each other, must be kept together by a very powerful force, which is the nuclear force. Of all the forces of nature, nuclear forces are among the strongest. In fact, gravity is one of the weakest forces in nature. You may think it's strong because it's keeping you sitting in your seat right now, but it takes something as large as the Earth with all its weight in order to keep you in your position. So gravity is considered to be a very weak force. Electronic forces are much stronger, and nuclear forces are much stronger still. So in atomic physics, which is the first thing that we will review for the MCAT exam, keep in mind that the aim is to harness the energy or force of the nucleus, which is extremely powerful. And once that energy is released, that energy can be used to do other things. Now, there are three important particles to consider that are released from a nuclear reaction: alpha particles, beta particles, and gamma rays. An alpha particle is a helium nucleus. So right off the bat, You can consider that as being positive and having considerable mass compared to the other particles which I will describe. The second particle, a beta particle, which is really more precisely called a beta negative particle, but nonetheless, if it's on the MCAT and they say beta particle, it is an electron. An electron has a much smaller mass, of course, than a helium nucleus, and it has a negative charge. And finally, gamma rays. Gamma rays are also released from nuclear reactions, and gamma rays have no mass whatsoever and no charge whatsoever, since they are a form of electromagnetic radiation, or light. You are now looking at the alpha decay of uranium-238. First off, you see here uranium-238. We have the superscript 238. The superscript represents the atomic mass number. The atomic mass number is the whole number closest to the atomic mass. Then we have the subscript 92. The subscript is the Z value. The Z value defines the element. It is equal to the number of protons, and the number of protons is equal to the atomic number of the element. There are three essential things to remember about alpha decay. To begin with, in alpha decay, we have the release of an alpha particle. And an alpha particle is defined as the helium nucleus, which is helium-4 So once you see that helium-4 has been released in the reaction, you know that you have an alpha decay. So that's the first thing you must know. The second thing is that notice that everything adds up, meaning that we have 238 going to 234 plus 4. We have 92 going to 90 plus 2. So it's very straightforward. The third thing for you to recognize is the importance of the Z value. And that is that the number of protons defines an element. If you change the number of protons, then you've changed the element. If you change the number of neutrons, it's the same element. Change the number of electrons, it's the same element. It's the number of protons that defines the element. If you were to calculate the number of neutrons in this element, you would simply take the 238 minus the 92, and that would equal the number of neutrons. And that goes for any element. Incidentally, the name of this particular element is thorium, but that is not important for the MCAT exam. We are now about to look at beta decay. You are now looking at the beta decay of carbon-14. Now, if you try to understand the idea behind beta decay, it is thus, that a neutron is decaying into a proton plus an electron. First, let us look to see if this equation is balanced. First, let's examine whether it's electronically balanced. On the left-hand side of the equation, we have a neutral particle. It's a neutron. On the right-hand side of the equation, we have a proton, which is positively charged, and an electron, which is negatively charged. So, both the left and the right side of these equations is essentially neutral. What about mass? Well, a neutron is slightly heavier than a proton, and an electron has a negligible mass. In other words, the left side of this equation is heavier than the right side of the equation. So what happens to the mass when we go from left to right? It's converted to energy according to the most famous equation of all time, which is E equals mc squared, in which mass is converted into energy. This is the energy used in nuclear reactions. So let's look at carbon-14 and how, in fact, a neutron is going to disappear and become a proton and an electron. Well, if we look at the left-hand side of the equation, we have carbon-14, atomic number 6, which means it has 6 protons. If we wanted to calculate the number of neutrons for carbon-14, 14 minus 6, so we end up with 8 neutrons. On the right-hand side of the equation, we have nitrogen. Why? Because the number of protons changed from 6 to 7. Therefore, immediately you must change the element. So nitrogen, 14 minus 7, we have 7 neutrons. And then, of course, we have the electron. The electron which is being liberated is indeed called a beta particle. So this is beta decay. We have 8 neutrons on the left-hand side of the equation, 7 on the right. 1 neutron disappeared. Where'd it go? It went into producing a proton. We have 6 protons on the left-hand side, 7 protons on the right. And the electron, which is liberated as a beta particle. It's very interesting because this is the way that nuclear reactions work. And so, what you can do, you can imagine taking compounds which nuclei will decay, releasing energy. Put these compounds underwater, and the energy released by these compounds will heat the water. The water will form steam, and the steam will rise. You create turbines that will take the steam, and the turbines start turning as the steam rises. The turbines are connected to generators, and those generators, of course, produce electricity. And so by harvesting the energy of the nucleus, we're able to create electricity. Here's a common MCAT question. Element A40 has a half-life of about 10 years. How much A40 is left from a pure sample after 30 years? First, we have to discuss what the definition of half-life is. So a half-life is the amount of time after which half of your sample has decayed. So if you have a half-life of 10 years, it means that after 10 years, you will have 50% of the material left from a pure sample. So 10 years has gone by, you have half, or 50%. Another 10 years go by, a total of 20 years, you have half of that, or 25%. Another 10 years go by for a total of 30 years, and you have half of the 25%, or 12.5%. The other way of calculating this is by using the equation. 1/2 to the power of n, where n represents the number of half-lives. So here, with a half-life of 10 years, and we're talking about a period of 30 years, so there's been 3 half-lives, 3 times 10, 30, 3 half-lives, so we're talking about 1/2 to the power of 3, which is 2 to the power of 3, which gives us 8, or 1/8. So 1/8, which is equivalent to 12.5%. A couple of little things about the MCAT, however. They don't tend to use precise numbers because they want you to be relaxed enough with your understanding of the concepts that you will be able to estimate when necessary. For example, they may put, instead of 30 years, 29 years. So it's not a stretch to estimate the 29 years as 30 years, which is able to give us a more rounded result in terms of the number of half-lives. So do expect that sometimes you may have to estimate. Of course, the equation for half-lives is quite similar to the equation for doubling time. Quite commonly on the MCAT, they'll ask a question about bacterial replication in the biology section. And instead of talking about half-lives, they'll talk about doubling time, which is just 2 to the power of n, which n represents the number of times that the bacteria will double. Now, we have reviewed the four most important aspects of atomic physics for the MCAT exam. The most commonly asked questions are alpha decay, beta decay, gamma rays, and incidentally, in terms of gamma rays, all they want you to know is that it doesn't have mass and it has no charge. And fourthly, half-lives. Now that we've looked at atomic physics, we're going to go from the atom to the movement of its electrons, which is electricity. We are now moving on to electricity. However, because many of the equations that are important in electricity and which you must memorize are very similar to the equations for gravitation, we're going to look at the equations side by side for two reasons. One, it will be more easy for you to memorize the two sets of equations, and secondly, you'll be able to see parallels between the two sets of equations. So first, electricity. F is equal to QE, one of the most fundamental equations. That is, the force in an electric field is equal to Q, the point charge, times E, the electric field. The relevant equation in gravitation is F is equal to mg. That is to say that F, the force in a gravitation field, is equal to m, the mass in the field, times g, the acceleration due to gravity. So you can see the similarity of these equations. Now, the most fundamental equations in motion comes from Newton's second law. And Newton's second law is that force is equal to ma, which is force is equal to mass times acceleration. So let's look at a derivation of that law. That is to say that acceleration is equal to force over m. And from the first equation, we see that F is equal to QE. So therefore, acceleration is equal to QE over m. In other words, the acceleration in an electric field is equal to the force over mass, that's Newton's second law, which is equal to QE over m. So this provides you the acceleration in an electric field. The acceleration in a gravitation field, we do the same thing. A is equal to F over m, which is equal to mg over m. Well, the m's cancel, and we just end up with g. In other words, we get the trivial result. And that is that when we have the acceleration in a gravitational field, that is simply equal to the acceleration due to gravity. Continuing with our comparisons of gravitation versus electricity equations, we will look at a couple of laws which, again, you must memorize. The first is Coulomb's law. And in Coulomb's law, we have the force in an electric field is equal to K Q1 Q2 over R squared. K is Coulomb's constant. Q1, Q2 are the 2-point charges involved. R is the distance between the point charges. Be very careful. On the MCAT, they will provide you with extra information that you do not require to solve a problem. You can bet they're going to provide you with information such as the radius of something. But this has nothing to do with the radius of anything. This happens to be the distance between the 2-point charges. In gravitation, the relevant equation is Newton's law of gravity. And it is that the force in the gravitational field is given by G, which is the gravitational constant, M1, M2, the two masses involved, and R, which is the distance between the center of mass of the two masses. Again, It has nothing to do with the radius. So notice how these two equations are remarkably similar. Both of them include the constants. Now realize that from what we mentioned about earlier, about how the forces of nuclear forces, electrical forces, gravitational forces are so different, clearly the constant for electricity would be a much greater number than the constant for gravitation, which is a much weaker force. Also, in terms of the MCAT exam, you don't have to worry about memorizing the constants K or G. They would be provided in the exam itself. But the structure of the equation is very important. They would rarely ask you to actually calculate something based on this, but a very common type of question would be to say something of the order of, if you have an electric field and there is a force in the electric field, what happens to the force if you double one of the charges? Well, if you double one of the charges, you would double the force because it's a direct relationship. Other typical questions is, what would happen to the force if you doubled the distance between the point charges or between the masses? It would be the same thing. It's an inverse square relationship. If you double the distance, 2 times r, then the 2 is squared, it creates 4. So if you double the distance, then the force will be 1/4. If you triple the distance, the force would be 1/9, which is 3 squared. So those would be typical manipulations that they would ask for the MCAT exam. Now, let's talk about work. We're going to talk about work in much more detail later in this series. But just in general, you could remember work as being force times distance. That's a very loose description of work, but it's comfortable for what we need to deal with now. And we'll talk about it in more detail later. So work is force times distance. So let us look at what the work is done in an electric field. Well, let's look at an electric field. First, I will draw some electric field lines. Here are some electric field lines. The understanding is that electric field lines are always drawn away from a positive charge. That's the standard. So it's as if there was a positive charge higher up, and therefore this is being drawn away from the positive charge. Clearly, if you were to put a negative charge here, because the positive charge must be up there, if you put a negative charge here, then that negative charge would be attracted to the positive charge, because opposites attract, and it would move in that direction. But let's imagine that we put a positive charge here. So positive Q. Well, like charges would repel, and this positive charge would be pushed away. But we want to push this charge towards the positive charge. We want to move it in this direction. If we move it in this direction, that will require work. That would require a force to push it in the opposite direction of the electric field. If we were to push this charge a distance delta y, then we can calculate the work done. Work being force times distance, and the force we saw earlier in electric field is QE. So work is force times distance delta y. So the work in an electric field is given by QE delta y. To be more precise, the QE is the absolute value. In other words, it doesn't matter what the charge is on the Q, whether it's positive or negative, if you are pushing it against the field, whatever the field may be, and you are doing work, work is given by the force times the distance. Well, let's look at what the work would be in a gravitation field. So in a gravitation field, let's imagine that we have an object. Here's our object, and it's on this surface. And this object is brought a distance delta y. Just very, 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 very slowly, it's brought a distance delta y against the gravitation field. Because imagine, gravity is working this way. Gravity is going to be pushing things down towards the center of the Earth. So we are taking an object and we are bringing it up. That's against the field. It's equivalent to moving the positive charge against an electric field. So as we're moving this way, we have work is equal to force times distance. The force, we said earlier, equivalent to QE, is mg. Of course, we'll be seeing a little later what we usually, the word we usually use for this is simply the weight of the object. So we have mg, and it's moving a distance delta y. So there we have work is force times distance. So now we've compared the equations for electricity and gravitation. All these equations must be memorized. Most importantly, you should understand any derivations that we've done, and to imagine, as I've mentioned, the different ways that these equations can be used. Now we're going to look at electricity more specifically. Electricity flows in circuits, and so we will look at the elements of circuits. The fundamentals include capacitors, resistors, and batteries. First, let us examine capacitors. The symbol for capacitance is C, capital C. The units for capacitance is the farad. The equation which you must memorize is the following. Q is equal to CV. Q, the charge, is equal to C, the capacitance, times V, the voltage. More specifically, Q, the charge, is in units of coulombs. So anytime we discuss Q, it's in units of coulombs. Notice that before, when we talked about Coulomb's law, we used a small case Q, and this is a larger Q. It's referring to charge, but it's only that the small case Q is referring to minute elements. So these are very small particles, thus they have small charges, whereas this Q refers to the total charge. Is equal to C, the capacitance, times V, the voltage. Voltage is in units of volts. And C, of course, in farads. We will look at a capacitor momentarily. Resistors. Resistors certainly resist the flow of current. Resistors come as a symbol R and the units ohms, also symbolized with the Greek letter omega. In terms of resistors, they are symbolized by what can only be described as a squiggly line. So this is the symbol for a resistor. Resistors can be hooked up in a couple of different ways. One is when they're hooked up one after another. Because one is after another, it is called in series. So if this resistor is R1 and this resistor is R2, if you want to calculate the total resistance of resistors in series, well then the R total would be equal to R1 plus R2. Resistors can also be hooked up like so. This would be called in parallel. If you wanted to calculate the total resistance across these resistors, it would be provided by the following equation. 1 over R total is equal to 1 over R1 plus 1 over R2. I have two things to say about this. First, common mistake that students make is to forget that this is the reciprocal of R total. So they'll put R total is equal to 1 over R1 plus 1 over R2. And then they make the mistake that way. So that's one way to make a mistake. The other thing is that you do have to practice this. Whenever you see this question, among the materials that you will be getting with this course, is very important for you to actually practice it longhand. Never use a calculator when you're practicing for the MCAT exam. There's no calculator on the MCAT, and you must practice your longhand calculations. It's a very important part of your preparation, because when you start getting, say, 1 over 3 and 1 over 17 as your fractions, then you have to find a common denominator and then use your basic algebra. Of course it sounds simple, but when you're nervous and you're pressed for time, that's when people make mistakes because they're not used to using their basic high school algebra. So very important to calculate out longhand. One other thing to mention about this is if you see something like this on the MCAT exam, it is not time to get nervous, because clearly this is simply resistors in parallel, identical to this, only that one of the wires is a little longer here and one of the other wires are a little longer there. That has no impact on your calculations. What the MCAT loves to do is take something that you're familiar with, that you've seen before, alter it slightly, and see whether or not you're able to adapt. And of course here, that would be no problem. Next, we'll talk about battery. The battery is given in units of volts. There are many other ways to symbolize the battery. Not just V, but also EMF. EMF stands for the electromotive force. It is the same thing to designate a battery. And the units, once again, is volts. Sometimes EMF is symbolized by the Greek letter epsilon, which is capital E. There are two equations that absolutely must be memorized, which are relevant to the voltage in a circuit. The first is V is equal to IR. That is, V, the voltage, is equal to I, the current, times R, the resistance. Current is in the units of amperes. We already said that V, the voltage, is volts, R is in ohms, I is in amperes. 1 ampere is equivalent to a coulomb per second. In other words, because current refers to the movement of charge, therefore the definition of an ampere is the amount of charge which moves past a point per second. The second equation that must be memorized is P is equal to IV. That is, P, the power, which is given in units of watts, is equal to I, the current, times V, the voltage. These two equations must be memorized. It's almost guaranteed that at some point on the MCAT exam there will be an equation that is based just on the use of these equations. So let us look at a basic circuit. We will start with this circuit in order to explain certain concepts. First off, we have two parallel lines. Two parallel lines in a circuit represents a capacitor. Now, if you were to take a capacitor and you were to place an insulator in the capacitor, then it is now called a dielectric. That is by definition. It would be then called a dielectric. So we also have in our circuit a resistor and finally a battery. So a battery is symbolized by two uneven parallel lines. The larger part or terminal is always defined as positive. The smaller terminal, negative. So anytime you see a battery, this is the first thing you can do to start labeling your circuit. Current is defined as the movement of positive charge. This is one of these 19th century errors that was started because people were trying to consider what is electricity. And initially, well, basically they had to guess. It's either the movement of positive charges or it's the movement of negative charges, because it is the movement of charge. And based on certain assumptions, it was thought that it was the movement of positive charges. We now know that electricity is the movement of electrons. And therefore, electrons being negative, that means that electricity is the movement of negative charges. But because of this essentially 19th century error, we are stuck with the definition that current is the movement of positive charges. And using this definition, we can still solve all problems with regards to circuits. So, when looking at the battery, after defining your terminals, we know where current would be emanating from. Current must be coming from the positive terminal. So we can say right away that here is our current, symbolized in this manner. Current I is leaving the positive terminal, coming along the wire, going up to this point here. This point would be called a junction. It's a point in the circuit where the current can go two different ways. Current can come along here and meet a resistor, which will resist its movement. Some current can come along here to the capacitor, and then the current would charge the capacitor. The current comes along here, positive charges here, and it starts to charge the capacitor. This terminal of the capacitor would start to become positive, this terminal of the capacitor negative. Now, would the opposites attract? Clearly, opposites attract. But the purpose of a capacitor is to store and separate charges. Therefore, these charges will not meet because the capacitor stores and separates the charges. So, when the battery is hooked up, the current will move in this way, charging the capacitor. Some of it current will complete the circuit and come along through the resistor, through the resistance in the resistor. Now, what happens is that when the battery is hooked up, the charge is going into the capacitor. If we were to stop the battery, if we were to unhook it, disconnect it, well then the charge in the capacitor would be released, thus discharging the capacitor along this long route here. It cannot go across here because that's the purpose of the capacitor, to separate the charge. Instead, it would come across in this manner as opposites are being attracted to each other. Now, what would be the purpose of this? There are many purposes for this. First of all, it has to do with current itself. There are two types of current that we use. One is direct current and the other is alternating current. Direct current provides a continuous level of current. Alternating current provides current that comes and goes, comes and goes. Thus, it is alternating. There are two important points to make with regards to the difference between alternating currents and direct currents. To begin with, a direct current, because it's steady and it's always there, compared to an alternating current which comes and goes, comes and goes. Clearly, the direct current will have a value which would be greater than the alternating current. And this can be calculated. In fact, when we talk about the alternating current, we don't talk just about the current level, we talk about the root mean square current. So we have I, RMS. That's the root mean square current. And that is equal to the maximal current divided by root 2. And of course, the value for root 2 is something that you should have memorized, which is 1.4. So the root mean squared is equal to the maximum current divided by root 2. Whenever we talk about batteries, you may have batteries for many household items. We're talking about direct current. That is current that is continually coming from the battery. When we talk about, for example, the current that comes to your home, when you plug something into the wall, that is alternating current. That is the way current is delivered to homes and businesses. That alternating current, we can calculate the precise current, which is the current but root mean square. One more thing to say about capacitors and the current that comes from it in terms of the value. When you have current going into sensitive equipment, for example your computer, if the current was always alternating on and off, that could be disruptive for your equipment. So that's why you'll have capacitors in the computer. It will steady the current. For example, when the current is on for this alternating current, it will run your computer and it will charge your capacitors in the computer. Then when the current goes away, your capacitors will discharge. Therefore, they will now run the computer. Then when the alternating current returns, it will recharge your capacitors and it will run your computer. So we see the value of the capacitor, charging it, and then it can release its charge, continuing to supply current to the circuit. The actual ability of the capacitor to separate and store charge depends on the separation of the plates, and it also depends on the size of the plates. You are actually thinking with a capacitor. This is a rather symbolic cartoon of a neuron or a nerve cell in your brain. And what we'll look at in more detail in biology is that in a neuron, the outer part of the cell, the exterior part of the cell's membrane, is positively charged. The interior part of the membrane is negatively charged. And so clearly, just by looking at this, that is what a capacitor is. It separates and stores charge. So the membrane is a capacitor, and it has a voltage associated with it, Vm, which is the voltage across the membrane. So the capacitor separates and stores charge, and so when, depending on certain elements that we'll look at in biology, when the capacitor discharges itself, it will send a signal along the neuron. So now you see the importance of a capacitor and how a circuit can work with a resistor and a battery. Now we're going to look at a more complex circuit and we'll solve it. And by solving it, you will be able to solve any circuit they provide for the MCAT exam. We will now look at a complex enough circuit such that by understanding the concepts involved in solving this circuit and knowing the equations, you will be able to solve essentially any circuit that they give you for the MCAT exam. The first thing to do when presented with the circuit is to label it. So we can see that there are two batteries, noted because of the parallel lines which are uneven. So we can label the batteries as epsilon 1 and epsilon 2. Epsilon representing the EMF of the battery, which is the voltage of the battery. There are 3 resistors, and so we will label them as well, and we'll give them original names such as R1, R2, and R3. So those represent our 3 resistors and our 2 batteries. So let's examine what will happen when this circuit is connected. Well, we have our positive terminal here, negative terminal there, positive terminal here, negative there, the larger terminal always being positive. And as we said before, current emanates from the positive terminal. So coming from the terminal will be the current, which we will designate as I. Because this current is coming from epsilon 1, we'll call this current I1. So I1, the current is coming from the terminal, passes through the resistor R1, and then comes here to this point. This point we'll call point A. Coming from the other terminal, epsilon 2, will also be a current, which we'll designate as I2. And this current coming from the positive terminal, coming along through the resistor R2, also gets to the junction at A. So we have I1 coming across this direction, I2 coming across this direction, hitting at this junction. So now we're going to have a new current coming through here, coming through this wire, because the 2 currents are coming from here. We have a new current coming through this wire. We'll call that current I3. As I3 comes down here, it hits another junction. This junction is B. Then we're going to have a current coming through this wire and a current coming through that wire. Now, I would like you to consider for a moment, you can put me on pause, but consider for a moment what would be the name of the current running through this wire. The current would have to be I1, and this current would have to be I2. And the reason for this is simple. The battery, which is generating the current, has a certain amount of current emanating from it and returning to it. The battery itself remains neutral. You can't buy in a store a positively charged battery or a negatively charged battery. A battery has positive and negative charges within it, but an equal amount of positive and negative charges. You can't buy a positively charged battery. And so the battery maintains its neutrality. So the current that leaves is the current that returns. We're going to look at that in more detail when we study electrochemistry in the general chemistry section of this series. But for now, it is quite clear that the battery must remain neutral. So now we've labeled the currents. There are only 2 laws that you must know in order to solve any of the circuits they can provide. These 2 laws are Kirchhoff's laws. Kirchhoff has 2 laws. The laws are, number 1, the sum of current is equal to 0 at a junction. Law number 2. The sum of voltage changes is equal to 0, and that is in a loop. With these 2 laws, you can solve any of the circuits that are provided to you. Let's start examining the first of Kirchhoff's laws. Sum of current is equal to 0 at a junction. First, we need to define a junction, which we mentioned before, which is an area where the current can have 2 different ways or possible routes. So these junctions would be twice in this circuit, which is at A and at B. So we have a junction here at A and a junction at B. The next thing we need to do is to define directions. When you do gravitational problems, at the beginning of the problem you need to define a direction for gravity. You say, for example, everything that's going down is negative. So then you know that if something is going up, it's got to be positive, and if something's going down, it's negative. You define it as such. In the same manner, we can define everything that goes into a junction as being positive and everything that's leaving a junction as negative. By sticking to this definition, then we will be able to solve the problems. So for example, at junction A, we have a current I1 which is arriving at the junction. We have current I2 which is arriving at the junction. So we will say I1 and I2 are positive. So we have I1 plus I2, both of them being positive. We have I3 leaving the junction. So then we will call I3 negative. Minus I3 is equal to 0. At the second junction, we have I3 arriving at the junction, positive, because it's arriving. Then we have I2 leaving the junction. We have I1 leaving the junction. So I1 and I2 are negative. Minus I1 minus I2. And that's equal to 0. Both of these equations are saying the same thing. By simple math, you see in both of these equations, it is saying that I3 is equal to I1 plus I2. You may be looking at this and saying, well, that's common sense. And it does make perfect sense, because examine what is happening here. We have I1 coming into the junction, I2 coming into the junction, I3 leaving. Clearly, I1 plus I2 must equal I3. And that is exactly what the equation is saying. Now, how could the MCAT trick you with such a basic concept of all the current coming into the junction must be equaling all the current that's leaving the junction? We'll examine this question. The currents and directions are as shown. What is the current that travels in wire P? You may want to take a moment and pause and consider what the answer would be based on Kirchhoff's first law. If we look at the currents, we have 2 amperes, an amp being the unit of current, 12 amperes here. Both of these are currents that are moving towards the junction. Here we have 7 amperes and 7 amperes moving away from the junction, arrows pointing away from the junction. So if we define everything as, and then we have wire P, we don't know if that's going towards the junction or away from the junction. We don't know. But we do know that Kirchhoff's law tells us that the sum of currents are going to equal to 0 in the junction. So we have 12 going into the junction, so that's positive. 2 going into the junction, positive. We have 7 leaving the junction, negative 7. Another 7 leaving the junction, negative 7. And then we have wire P. And all that is going to equal to 0. Well, 12 plus 12 is 14. Minus 7, that's minus 14. So we have 14 minus 14, well, that's 0. So then P is equal to 0. The current in wire P is equal to 0. So the amount of current that goes into the junction is already equal to the amount of current leaving the junction. So that means there must be no current going through wire P. So all they do is take something that you already know, change the angles or change the way it looks to see whether or not you truly understand the concept. Well, now let us look at Kirchhoff's second law.